Okay, in this video, we're going to look at constructing confidence intervals for mu when sigma is known. Okay, and what we have is a margin of error, okay, which is E equals Z star times sigma sub x bar. Okay, and remember this all hinges on using the central limit theorem after constructing a sampling distribution of sample means. Okay, and the sigma sub x bar is equal to sigma over square root of n. Okay, so the margin of error is Z star times sigma sub x bar. And our confidence interval itself is our x bar, which is our sample mean. So we're going to take a sample of size n, find the mean of those samples, and then add or subtract Z star times sigma sub x bar. Z star is sometimes referred to as a critical value, and it's a Z-score that corresponds to our level of confidence C. Now in previous examples, okay, or previous videos, okay, we saw that we used, if you had a 95% confidence interval, we used a Z star value of 2. Okay, I didn't actually call it Z star then, but we basically said we were 2 standard deviations from the mean. Well, 95%, that was using the empirical rule, saying that 95% of the data was within 2 standard deviations of the mean. Now that was an approximate value. Okay, what we're going to do now is get a little more formal with it and get more exact values by using our tables in the normal distribution in the Z tables. Okay, so the way we interpret those answers for our level of confidence C, if we were 95% confident, okay, then if our confidence level is 95%, we would say we're 95% confident that our interval contains the population mean mu. Or we would expect 95% of the confidence intervals that we construct to contain the true value of the population mean mu. Okay, so that's how we interpret the answers or our intervals. Okay, so common confidence levels are 90, 95, and 99%. And the basic idea there is that when you make a prediction or estimate about the population mean, you want to be confident in your answer. You don't want to be like 50% confident. Okay, you want to have a high confidence in your answer. So these are the most common ones, 90, 95, and 99. You'll also see 98. Now we previously used 99.7 because that was the empirical rule said that 99.7% were within 3 standard deviations of the mean, and that allowed us to use 3 for our Z star value. But again, we hadn't actually discussed Z star and actually what it meant until now. Okay, so there's going to be a different value we use for 99% compared to 99.7%. Okay, so 99% level is much more common than saying a 99.7. Okay, so what is that? Where are those critical values for Z actually coming from? Well, remember that a confidence interval is basically having x bar, your sample mean, right in the center of it. Okay, so on your x bar axis, you're going to take whatever your sample mean was. That's just one of your sample means, like x bar sub 1. So you took one sample of size n, you found that, plotted on the axes. Well, when you do plus or minus Z star times sigma sub x bar, you're adding and subtracting the same value from x bar. One of them is going to be on the left-hand side, the other on the right-hand side. But what's important here is notice that x bar sub 1, or your sample mean in this case, is going to be halfway between the endpoints there. So what you're really looking for is what Z-score is symmetric on the left-hand and the right-hand side of x bar. Okay, so you're looking for the middle 90% of the data, the middle 95% of the data, or the middle 99% of the data. So how do you actually find the middle 90% of the data? I already have this worked out, okay, just for the sake of time in drawing this. Okay, and you've already done this before, back in the normal curve content section. But to find the middle, students have a hard time with this a lot of times. To find the middle 90% of the data, again, a Z-score of 0 is going to be right in the center. That's wherever your x bar value would be, your sample mean. You're going to be 0 standard deviations from the mean there. So you have 90% in the middle. Means you have 0.05 on either tail. Okay, to the left of this Z-score, whatever it is, and then to the right of whatever this Z-score is. Now I have the values on there already, 1.645 and negative 1.645. Well, where those are coming from, if you have the middle 90% of the data, you don't look up 0.9000 in your table. What you look up is the area to the left of one of your z-scores. Well, the area to the left of this value right here, where I have negative 1.645, but again, we don't know that yet, but the area to the left of this z-score is 0.05. Again, it's because you split 10% by 2, or 0.1 by 2, and that gives you 0.05. So that's the value that you look up. In your table of values here in the body, we're looking at 0.05 area, or 5%. So when you do that, notice that we are halfway between 0.0505 and 0.0495. Now your book will actually use 1.65. Other teachers or other books will actually average those two together because 1.645 is exactly going to be halfway between these two values. So 0.0500 is exactly halfway between these two. So if you take halfway between these two z-scores, negative 1.64 and 1.645, okay, you get 1.645. Now, as long as you show your work, as far as what you put in for the z-value, I would accept either one, using 1.645 or 1.65, because different books will do it different ways. Okay, so those are the z-scores, or the critical z-value for the middle 90%. Now, it doesn't matter if you use negative or positive, because in your confidence interval, you're going to do plus or minus anyway. So that plus or minus is already taken care of. 1.645 is the critical value. The middle 95% is actually 1.96. And you can see 99% is 2.575. Okay, and again, I'll just show you the curve on those. The middle 95% means you have 5% left over to split between the two ends. So that's 0.025 on each end. So when you look up 0.0250, okay, 0.0250, okay, that number occurs exactly in the table at negative 1.96. So that's your critical value for z, negative and positive 1.96. For the middle 99%, that means you have 1% to split between two ends. So there you're looking up 0.005 on each end. Okay, and when you look that up, you're exactly halfway between these two values here, 0.051 and 0.049. So similar to the 90% interval, you're exactly halfway between these two values. So 2.57 and 8, take the average of those two, is 2.575. Now again, your book may use 2.76, okay, which is okay. Okay, so that's how you find the values for the critical value z. If it was a 98% confidence interval, then you would have 0.01 on each side. And you would look up 0.01 area and find the z-score for that. Okay, so to use the z-scores for z star, and by the central limit theorem, we must have an approximately normal distribution or a large enough sample size that n is greater than or equal to 30. Okay, so an example I give you, a random sample of 32 days during a recent year, the closing stock price of a company has a sample mean of $41.50. If this population standard deviation sigma is $2.42, construct a 90% and a 99% confidence interval for mu. Okay, so again, the idea is to construct a confidence interval for mu is that we only have 32 days that we took the sample for, and we're trying to say, based on that, where do we expect or where would we predict mu to be? Right now, our best estimate for mu is 41.50. But because we took a sample, we have to have a margin of error included in that. So our margin of error deals with how varied, or the standard deviation, how spread out our original data set was. Okay, so now, when you look at x bar plus or minus z star times sigma of x bar, again, this is really just plug and chug. We're going to do a 90 and 99% interval. Okay, so again, I have these answers already worked out. Okay, so I'm just going to slide those down. So for the 90% interval, I'll show you this here. You take your sample mean, which was 41.5, plus or minus z star times sigma sub x bar. Well, again, for a 90% confidence interval, that was a z star value of 1.645. And then your sigma sub x bar is sigma over the square root of n. So 2.42 over the square root of 32. Okay, so basically this comes down to picking the values out of the question for x bar, the z star value, and the standard deviation in n. Okay, and it's pretty, I don't say easy, but self-explanatory when you read the question. Okay, it shouldn't be too crazy to find the values they're giving you. A sample mean of 41.50, that's saying x bar equals 41.50. They're giving you sigma is 2.42, so that's sigma over square root of n. Well, they had 32 days, a random sample of 32 days. So n is 32. Okay, and again, I like to see the estimate for the margin of error. I shouldn't say estimate. I like to see the margin of error, and then your interval estimate, okay, written out. Okay, you can write it in two different ways. One is using the interval notation, 40.796 to 42.204. You put the smallest number first, the largest number second. Okay, so when you subtract, that'll give you the smallest number first. Then when you add the margin of error, you get the larger. Okay, or you can write it as mu between those two numbers. Okay, for the 99% confidence interval, okay, what changes here is your z star value is now 2.575. Or if you use 2.58, that would be acceptable. Okay, and as far as the rounding goes on these, the general round off rule is you go one place farther than your original data. Okay, but you can also look at how many decimal places kind of make sense. Like you don't want to, like this is in terms of dollars here. So if you rounded that to the nearest cent, then I would accept that. Now I just went one more decimal place than the nearest cent. But again, that's not something to go too crazy with the round off rules. What you wouldn't want to do, you wouldn't want to round this to just 1. Okay, the margin of error to 1. Okay, you don't want to do that. Okay, so there, we're 99% confident that our interval 40.398 to 42.602 contains the true value of the population mean. Okay, so those are both estimates for mu. Now what I'll point out is that notice that the more confident we got, we went from 90% confidence to 99% confidence, and notice what happened to our interval. The lower bound of the interval went from 40.796 to 40.398. Okay, so the more confident we got, the lower our lower bound went, and the higher the upper bound went, 42.602, where for 90% confidence it was 42.204. What I'm getting at is that when we became more confident, our interval became wider. And the basic idea there is why did that happen? Well, notice that 41.5, that's the center of each of the intervals. That's the value we started with for x bar. The only thing that changed in our computations was the z star value. So the more confident you are, the more area you have in the middle of the graph. So 99% of the area is more than 90% of the area, which says you're going farther out to the left and right in the 99% interval than you are on the 90% interval. Okay, now in layman's terms, that's basically saying if you're going to make a prediction about something or an estimate, and you want to be more confident in your estimate, you have to allow more values into your interval. So if I were standing in front of a class and I wanted to estimate their average age, so the population age for that class, if I said, okay, I'm 90% confident that your age is between 20 and 20, that the average age is between 20 and 21 years old, then I probably shouldn't be that confident in saying that, because 20 to 21 is a pretty small window or a pretty small interval when you're looking at average age of students. But I could be much more confident in saying that the average age of students in this class is between 15 and 40. So notice if I allow more values into my interval estimate, then I can say that with more confidence. Okay, so that's the basic idea of what's happening here. Okay, mathematically, again, it's just because your z star value is larger, the more confident you are. One way you counteract that, okay, if you want to kind of make your interval shrink again, well, what would make your interval smaller here? If you want to be 99% confident, so that 2.575 is stuck there, the 2.42 is stuck because that's your standard deviation for the population. Okay, they're going to give that to you. What you can do is change n. If you take a larger sample size, when you do sigma over the square root of n, if n gets larger and larger, that means you're dividing, in this case 2.42, by a larger number, which makes your answer smaller. So one way to counteract becoming more confident, because it's always good to become more confident, is to take a larger sample size. Okay, the last example. We have a mean of 50 runners for a regular run of 5K. Was found to be 22 minutes and 38 seconds. We know the population standard deviation is 2 minutes and 15 seconds. We're going to construct a 95 and a 98% confidence interval for the population mean of all runners. Okay, so this one has a little trick to it at first. They give you the times in minutes and seconds. So you got to be careful with that because the units are not the same. Okay, one's in minutes and one's in seconds. Okay, so what you have to look at is converting either to just minutes or just seconds. Now, just because I already have this worked out, what I did, I converted 22 minutes and 38 seconds into just minutes. Okay, and the way you do that, 22 minutes and 38 seconds is 22 and 38 sixtieths minutes. So basically you take the number of seconds, divide by 60, because there's 60 seconds in a minute, and that'll give you the decimal value of 0.633 for 38 seconds. Okay, so 38 seconds is equivalent to 0.633 minutes. 30 seconds will be a 0.5 there, okay, because 30 seconds is half a minute. 15 seconds, which shows up in the next one, is a quarter of a minute, so that's a 0.25. Okay, so 22 minutes and 38 seconds is 22.633. Now that is rounded. Okay, it actually repeats. Okay, 0.633 repeating. And 2 minutes 15 seconds is 2.25 minutes. Or what you could do is convert the minutes into seconds. So you do 22 times 60 and add the 38. Do 2 times 60, add the 15. And then you could express your answer in just seconds instead of minutes. Okay, it doesn't matter which way because it wasn't specific here. So to do a 95% confidence interval and a 98% confidence interval, again, you're going to take your sample mean and add or subtract z star times the standard deviation of the x bar distribution. Okay, so I'll put the (95% confidence level up there. You take your sample mean, 95% confidence is a z star value of 1.96 times the standard deviation, which was 2.25 minutes, divided by square root of n, which was square root of 50, because there were 50 runners. The 5K in this question has nothing to do with the numbers in the actual confidence interval. Okay, so we get approximately 22 to 23.257 minutes. Okay, so we're 95% confident that our interval 22.009 to 23.257 contains the true value of mu.